The other topic that we need to deal with is the topic of bounds. So let's go back to our original problem, maximize x1 plus 2x2, and we have x1 plus 3x2 less than or equal to 16, and x1 plus x2 less than or equal to 7, and then we had x1 and x2 had to be greater or equal to 0. Now imagine that we are given some additional constraints also, that x1 has to be between 2 and 1, and that x2 had to be between 3 and 2. Now, without any additional knowledge, what we would do is we would then add x1 less than or equal to 2, and x1 greater or equal to 1, and x2 less than or equal to 3, and x2 greater or equal to 2, and add these constraints to the problem, to the model. But this would imply that if we had, let's say, if we had 100,000 variables, 100K variables, and we had 50K constraints, imagine that each of these 100,000 variables had an upper and lower bound. Then this would imply would have 250,000 constraints. Okay, because each of these variables then generates 2, that's 200,000, and we get 250,000 constraints, which makes the computational time for solving this problem a lot longer than the original problem. So researchers were looking and saying, was there anything we can do to avoid that? So their objective was to, is there a way to incorporate bounds without expanding the number of constraints? And the answer is yes. And the way they did this is they modified the departing rule. So whenever the entering rule is the same for which departing rule modified the departing rule of simplex. Okay, so if a new variable joins the basis, so one in the existing basis has to leave, and how do you decide? Well, the rule is modified. And also what they did is modified, so they modified two things. They modified the departing rule, and they also modified the definition of a basic and a non-basic variable, of non-basic and basic variable. Well, we are not going to cover the rule, but we're going to cover how the definition of non-basic and basic variable changed. So before, we have that a non-basic variable is always equal to 0, and a basic variable, to allow for degenerate solutions, is greater or equal to 0. Most of the time it's positive, but we do encounter occasionally a basic variable that is 0. Well, as mentioned just before, in network simplex, degenerate solutions are pervasive. Okay, so now if we have suppose that we have xi is between some upper limit and some lower limit. Okay, so like we had 1 and 2 and 2 and 3, suppose that every variable has an upper and lower bound. Okay, now our definition will be that a non-basic variable has xi either the lower bound or xi is at the upper bound. So if it's not basic, it's definitely either at the lower bound or at the upper bound. So notice that before Li was equal to 0 and ui was infinity. So we had that a non-basic variable is equal to 0. But now we're generalizing that now so that a non-basic variable is either at the lower limit or at the upper limit. So the basic variables are so that's the definition, non-basic. The basic variables, if a variable is basic, if xi is basic, then xi will be somewhere in between. Now, generally, it will be floating. Okay, so we would call this floating. So if it's at the end points, then it's non-basic. If it's in between, then it's basic. Now notice that degeneracy causes the less than or equal signs. So we'd like to be able to say that it's xi strictly greater than li and strictly less than ui, which you would like typically, but because of degeneracy you also have to allow, just like we allowed here, greater or equal to 0, we now allow here less than or equal to signs. So we will see this. We will refer to non-basic variables when they're at their endpoints and basic variables when they are floating, but they could also be at their endpoints. This is the concept that we will be using, and we can move on to some of the other things.